Good morning, everyone. We're here for the MICD Catalyst showcase for this year, and I'm Mariana Carrasco. I'm the MICD Associate Director, and I'm gonna give some housekeeping notes before we get started, and it's just two quick ones. You won't be able to talk, so no audio or video from you, but if you want to ask questions, on the left-hand side of your screen, there's a Q&A box where you can ask questions, and one of us will read it to the speaker for them to answer. And the second thing is that the session is being recorded. So now I'm going to hand it over to MIC Director Krishna Garikipati. Thank you for attending.
Okay. Hi, everybody. Good morning, and I will skip the now mandatory reference to these unprecedented times and move on. But anyway, as I said, thanks for joining us. As you can imagine, this is an abbreviated version of what was to be our MICD symposium. We'd always planned to have these Catalyst grant talks as part of it. That it was to be an important part of the symposium. And we decided that since that part is really internal to the university, it sort of showcases what's actually happening at the university, the research that's happening around MICD with many of our affiliates and many people even joining MICD to participate in this sort of research and these sort of grants. It really made sense to go on with it. So that's where we are. The Catalyst grants are now in their fourth year, and we've had between 4 and 7 grants awarded in each of the years 2017 through 2019, and we'll have the program announce more awardees later this year. And so what we have today is two sessions. Each session has 3 talks by groups that have had Catalyst grants or that have Catalyst grants even now. The first has the speakers and the presenters in the first session are Robert Krasny from mathematics, followed by Vikram Gavini from mechanical engineering, and then Yulin Pan from naval architecture and marine engineering. So Robert Krasny, we'll start off with him in just about a minute. He is, as many of you know, probably all of you know, Robert Krasny is a professor of mathematics. His project comes from the 2017 cohort of the Catalyst grants. So that was the first year in which we handed out Catalyst grants. I believe you can all already see his slides, and you can see Robert sitting under his slides. And I will then mute myself and take it away. I'll just make one statement. I'll just repeat what Mariana said. To please put your questions in the Q&A. Mariana or I will, on occasion, interrupt Robert if we think the question needs to be answered right away, or we'll save them up for the end. We will just use our moderator's prerogative to decide on that. Okay, so we're ready, and I will invite Robert to take it away.
Thank you very much, Krishna, and good morning, everyone. And I'm going to tell you about integral equation-based methods for scientific computing. And we had a postdoc, Ling Xu, working on this. And there are currently 3 AIM PhD students. AIM, that's the Applied and Interdisciplinary Mathematics PhD we have here in the math department. It requires 2 co-advisors, one in math, one in a partner discipline. And Leighton Wilson is co-advised by Paul Zimmerman in chemistry. Nathan Vaughn is co-supervised by Vikram Gavini in mechanical engineering. Brian Sandberg is co-advised by Alec Thomas in nuclear engineering radiological sciences. And so the outline today, I'm going to begin with an example, the Poisson equation, and then I'll talk about fast summation methods and our barycentric tree code, and then some applications first to electrostatics of solvated proteins, and then incompressible vortex dynamics. So the example that I will use here to introduce the topic is a Poisson equation. So imagine there's a charge density, rho, on the right-hand side, and we want to solve for the electrostatic potential. And in a simple form, it could look like this. And so it's a differential equation, and the standard procedure is to discretize the differential equation and then invert the linear system that results. Okay, and so there are many, many ways of discretization. I've written down a finite-difference scheme over here. Just as, this is a very sort of high-level overview. You would first discretize the differential equation, and then you'd be evaluating phi at some grid point. You'd have the charge density at that grid point, and you want to solve. This is now a linear system of equations, and that has to be inverted. Inverted in quotes means we're just solving for the solution of the linear system. Now, there's an alternative approach, the integral equation-based approach. And so we reverse the order of these operations. So first, we invert the operator, and then we discretize. And so what it boils down here is that the inverse of the negative of Laplacian is given by a Green's function, and the phi I can be evaluated at some point xi with this convolution integral. So it's a convolution of the charge density with the Coulomb potential. And then we discretize this integral. You see, it's the reverse order. And in the end, we need to evaluate something like this. So these QJs would come from the rows and maybe some integration weights, etc. Okay. And so this is another way to solve the Poisson problem. Now, there are some disadvantages to the integral equation-based approach. And first is, for example, you have to do a loop over I and a loop over J. And so the O of n squared cost is a disadvantage. We also need to compute singular integrals over here, you see, and so that presents issues as well. I'll focus today on the cost issues, but a lot of work has been done to reduce the disadvantages. There are potential advantages. Okay, so the inversion is done analytically, and so potential advantages I would include the ability to deal with complex geometry, say, more conveniently, as well as to do adaptive refinement. Okay? I say potential because we're still, say, in the process, we meaning the people who work on integral equation-based approaches, we're still in the process of, let's say, realizing these potential advantages, but they are there. I'll continue now. So I'm going to focus on this issue with the O of n squared cost. And so we need a fast way of doing these sums over here. And so these are fast summation methods. Here's the objective, is to evaluate phi I given by this expression. And so there are particle mesh methods, particle in cell, particle-particle, particle mesh Ewald. And these methods more or less think of projecting the charge density here, which is at some points xj, projected onto a regular mesh, and then often use an FFT to do the calculation. On the other hand, there are tree-based methods that do not use FFTs. And among these, I'll cite the fast multipole method by Greengard and Rocklin, and then a tree code by Barnes and Hutt. These methods have some important similarities, but also important differences. And the tree code is the focus of the work that I'm presenting here. So the idea of the tree code is as follows. The particles, we can think of them over here, and they are not necessarily on a regular grid, but they're subdivided into a hierarchy of clusters. And so at level 0, there's a single cluster. Level 1, there are 4 clusters in 2D. Level 2. And you see, if a cluster contains no particles, it doesn't have to be subdivided. And so at the end, we have a system, a hierarchy of clusters, and then particle-particle interactions. So I think of this as the interaction between particle xi. Think of that as a target particle, and xj as a source particle. And the exact particle-particle interactions are going to get replaced by particle cluster approximations. So for example, a particle, say this particle over here, is well separated from this cluster up here, this cluster over here. And when a cluster of particles is well separated from a target, there are approximations that can be used. Okay. Now, of course, this particle is not well separated from other particles, but if you go to the next level in the tree, then that particle might be well separated from some other clusters. Okay. And so this can be organized in such a way that the operation count is reduced from order n squared to n log n at the cost of introducing some approximation error, which can be controlled. So let me say more about how these approximations are done. And so I'll give 2 examples over here. The fast multipole method traditionally used spherical harmonics. So for the Coulomb potential, with a target x and a source y, can be written this way. There's a double sum over indices. We've got spherical harmonic functions over here. And you see Rx, theta x, phi x. Those are the spherical coordinates of the target x. And then over here you see the Ry, theta y, and phi y. Those are the spherical coordinates of the source. Okay, and n up here controls the accuracy of the approximation. An alternative that we use now, we've been working very recently now to develop a barycentric tree code. It's based on polynomial interpolation. So the Coulomb potential can also be approximated by this expression, which is for each fixed x, it's a polynomial in the variable y. Okay, and this is a 3-dimensional tensor product of one-dimensional polynomial interpolants. The L functions here, the L function is a traditional conventional Lagrange interpolating polynomial. And y1, y2, y3, those are the Cartesian coordinates of the y point over here. The x is the same. Sk are the interpolation points. Okay, so you pick some interpolation points. In this formula, if we plug in y equals sk into this formula, it will reproduce the value here at the Coulomb potential. And that's due to the properties of these Lagrange polynomials. So this is just a 3D version of polynomial interpolation that learned in a first numerical analysis class. Now you also learn a conventional form for the Lagrange polynomials, okay? But we don't use that. We use what's called the barycentric form. And I learned about that from a paper by Jean-Pierre Beroux and Nick Trefethen in Science Review in 2004. They wrote about the barycentric form of polynomial interpolation. And in that case, the L functions over here have this expression. Okay, this is a barycentric form for the Lagrange interpolating polynomial. It's not very familiar to people unless you read this review paper, or have seen it in some other context. This form has some important advantages, and those involve using Sk. This is in one dimension. Sk will be the Chebyshev points. So I'm skipping over many details just to give you a sketch and the flavor of what's going on. A former student, Lei Wang, and a former postdoc, Svetlana Tulupova, and I wrote a paper about a barycentric tree code. So the idea is to plug this expression over here, this approximation gets plugged back in over here, and et cetera, we get a barycentric tree code. Now, the point I want to make is that the form of the approximation is the same as the exact kernel over here. We're replacing a Coulomb potential with a singularity at y by, let's say, several Coulomb potentials with singularities at sk. Turns out that that's very well suited for GPU implementation, and in a way that other approximations are not. And so that's what I want to tell you next. The GPU accelerated barycentric tree code is something that we recently developed, and so here's an example of so of course GPUs have this property of being massively parallelizable as long as those operations can actually be done synchronously and are not too complicated. And this barycentric tree code is very well suited for that. So with 1 million random particles in a box using the Coulomb potential, you see results here. You see runtime on this axis and error on this axis. This is evaluating the potential at 1 million points, self-induced by the distribution. The results on top here are for a 6-core CPU. And the results on the bottom here are for a single Titan V GPU. And so the line that goes across is direct summation. So that would be the cost of the O of n squared operation. On the CPU, it's up here. On the GPU, it's way down here. So the direct summation parallelizes very well on GPUs. And the dashed line is like probably 200 or 300 times faster than the solid line over here. The tree code results are these results over here. Now, there are several parameters in the tree code. One is the degree of the approximation, and those are what these symbols represent. So higher degree increases the runtime a bit. And there's another parameter which I haven't told you about, but that determines when a particle and a cluster are well separated. Okay, and so with 3 different values of the parameter, we can say efficiently get down to machine precision. Still beat direct summation. Now that's on a CPU. Barycentric tree code is implemented now on a GPU, and it's beating direct summation by a fair amount. So these results were obtained. Nathan Vaughn and Leighton Wilson, current students, they took the parallel computing class that Quentin Stout offers. They attended the NVIDIA hackathon. They were able to implement this tree code. So there's a paper going to appear about that. They've also set up a GitHub site where we've put the barycentric tree code as well as our previous tree codes on there, and we welcome people to check that out. Now with this tool, now we can solve some application problems. So first I tell you about electrostatics of solvated proteins. So imagine schematically domain omega 1, that's a protein domain, to be the interior. And on that domain, we want to solve a Poisson equation where we have some dielectric constant representing the protein domain, and then we have some point charges representing the atoms in the protein. And then the exterior is domain omega 2, that's the solvent. Okay, it's a dielectric continuum with an epsilon 2. There's also a linearized Boltzmann distribution of charge, where this kappa bar represents concentration of mobile ions, neutral, say positive and negative species in the exterior of the protein. And then gamma is the interface, that's the molecular surface. We've got continuity of the potential, continuity of the electric displacement on the interface. A far field boundary condition on the electrostatic potential. So the objective here is to solve for phi, and we can convert these PDEs here to integral equation form. It's an integral equation on the interface, gamma. We solve for the potential. From that, we can get the salvation energy, and that yields biological information about the salvated protein. Skipping lots of details, you can understand why. Here is an example. This is protein 1A63. It's the RNA binding domain of E. coli Rho factor. It's got 2,069 atoms. Here's a schematic of it. We triangulate the molecular surface, in this case with 132,000 triangles. We solve for the salvation energy or electrostatic salvation energy. With this number of triangles, we can get error at 1.3%. This is a plot of the computed potential on the molecular surface, negative and positive values. So plots like this are used by people in biochemistry to understand things like binding and enzymatic activity of proteins. Now, these are old results, but I'm going to cite them. The tree code was able to compute the solution, and this is on a single core, by the way, 368 seconds using 149 megabytes. APBS is the adaptive Poisson-Boltzmann solver, one of the popular finite difference methods that's used. It's available and it's used very widely. It took 1,647 seconds. It used 11 gigabytes of memory. And so to achieve this level of error, the tree code is Weiwa Gang is a former postdoc with me, and we wrote a paper about that. But this is continuing now. And most recently, a paper appeared in the journal Protein Science. They had a special issue called Tools for Protein Science. And the article was Improvements to the APBS Biomolecular Software Suite. So the people in charge of APBS, that's principally Nathan Baker that you see down here. He's at the Pacific Northwest National Lab. He's the original developer, and he maintains APBS there now. And he's developing it into a software suite. So he's accepting contributions from different groups. And he put together this overview of the contributions in there. So Leighton Wilson and Jiawei Chen was a student of Weiwa. Weiwa is at Southern Methodist University now. So these two students went to the PNNL over the summer, and they converted our Fortran code to C, installed it, and we now are part of the APBS software suite. I want to talk about another application to incompressible vortex dynamics. So in this case, omega is the vorticity, and psi is the stream function. And the vorticity is a vector. This is the Euler equation. The velocity is incompressible. Stream function is related to the vorticity by a Poisson equation. And the velocity can be recovered from the stream function. So, when I see a Poisson equation, how I like to solve it. We solve it with the Green's function, and then we differentiate to get the velocity. So the velocity is given as an integral. It's the Biot-Savart integral. And it's discretized, and then we use a point vortex method where the point vortices are vectored by their self-induced velocity. I'll show you two examples. First, an elliptical vortex that Ling Xu computed, and then disruption of the polar vortex. Pete Bosler was another AIM PhD who was co-advised by Christiana Jablanowski. So first, the elliptic vortex. On the left, you see a vorticity distribution. This is on a log scale down here. So there's a flat, almost flat plateau at the center. The vorticity is positive. So this is going to rotate counterclockwise. We use an adaptive particle distribution. And so at time zero, the scheme detects where the vorticity has a larger variation. And let me show you how this evolves in time. Hope I'll get the movie. I need to turn off. Maybe I need to turn off the laser pointer. Yeah. The vortex rotates, and maybe I'll just stop it in between. So the point vortices are chosen adaptively every interval of time, and it's chosen in such a way that it captures the fine details in the vorticity distribution. In particular, see this plateau over here has some waves developing in it, which the scheme captures. And a lot of these details, I think, have not really been well resolved in the past. You see, well, let me go back. Didn't them to clicked. Okay. Yeah, I'm just going to let it run.
Robert, while that's running, you have about 9 minutes for your overall
You have
time.
9 minutes. Okay. All right.
Well, that's for the overall time. About 5 minutes maybe to the end of the talk. But
yeah, that's what I thought. Okay.
okay, good.
Well, there are these waves radiating in the exterior. Those are at low amplitude, like 10 to the minus 3. I don't think those have been seen before. So we're interested in examining these vortex dynamics. I want to show you another example of vortex dynamics. This is now on a sphere, and this is what Pete Bosler did. He computed the disruption of the polar vortex. So Jukes and McIntyre did a simulation of that in 1987. We used the barotropic vorticity equation on a rotating sphere. I think I misspelled barotropic here in this context. And so its rotating sphere has a Coriolis effect, which changes how the vorticity evolves in time, but it's still a vortex method of the sphere. And the vorticity here is in red, and this is the polar vortex, but the North Pole, the axis has been tilted, so we can see the North Pole over here. And this would be a steady solution. It would just rotate. But in this problem, the right-hand side, we introduce a forcing function. That's what Jukes and McIntyre did. It pushes the polar vortex off the axis, and then the forcing turns off, and the polar vortex is allowed to evolve. See what happens. Here's what this simulation does. So there are details here that resemble what can be seen in satellite photographs, but we have more work to do to analyze these results. So I'm telling you now a summary. I talked about integral equation-based methods for scientific computing. It's all about particles and fields. And so in this approach, the fields are computed by convolution with the Green's function. And we use adaptive particle distributions to get good resolution. We use a GPU-accelerated barycentric tree code to make it efficient. Current projects in electrostatics, Leighton Wilson works, one of these projects is protein pKa, protein ligand binding energy. I see attraction and repulsion of charged dielectric spheres. The reference interaction site model is a 3D RISM. The IFCI, this is the incremental full configuration interaction model. This is for quantum chemistry. This is something that Paul Zimmerman has developed. Leighton is in the process of adding, with one of Paul's students, is in the process of adding implicit solvent to that. Electronic structure, I haven't told you anything about, but Nathan Vaughn is working with Vikram Gavini to do an integral equation-based approach for cone-sham density functional theory. Ryan Sandberg works with Alec Thomas for collisionless plasma, described by Vlasov-Poisson equation. Continue with incompressible flow, Ling Xu, my former student Monica Nietzsche, adding viscosity, solid boundaries, extending it to 3D. Here's my contact. If you'd like to discuss and learn more details, please contact me. Especially we're interested in collaborations. Feel free, we can have a chat. Thank you, I'm done.
Thanks very much, Robert. I'd encourage attendees to put in questions, but then I could probably get things kicked off. We have a few minutes. I actually have two questions. The first is related to the barycentric form of the Lagrange polynomials. So I guess, so obviously the form is the same. The form is different, but ultimately you retain the same polynomials. Now, what are the advantages that this delivers for the tree code methods?
Okay, for the tree code method, you see, for example, over here, you have to evaluate these spherical harmonics. Those are done with recurrence relations. That's not conveniently done on CPUs, on GPUs. This form over here, this looks just like the direct summation, right? The direct summation is a sum over, it's just evaluation of this formula where I and J runs over, some indices. This expression here looks like a direct summation over these new particles, and so it's very well suited for GPUs.
I see.
That's what I'll say.
But the barycentric form over the traditional
this form over here.
Yeah. So what?
So the other thing is these can also be, that's a separate step, but these can also be conveniently evaluated because these form, for example, here's a sum, and this is a sum with very simple arithmetic. So that works well on a GPU. And then you just have to divide by this thing over here. So I mean, it's very simple arithmetic here. It's not calling any special functions. It's all tremendously. You see, the other thing is each term over here is independent. So for each choice of K1, K2, K3, these terms can be computed simultaneously. So there's no recurrence at all here, and that's why for each K1, K2, K3, that's like a different thread on the GPU.
Oh, I see.
At the end, you have to do a reduce to add them up, but it just, I mean, if you try to implement something like this, it gets much more complicated and not this. I would say though that this required some very good programming, but in the end, it works, I would say.
Okay. And we have a couple of questions from the audience.
Yes.
From Jessica Peselatro says the polar vortex problem he's seen a spectral DJ code simulate this. Can you comment on any improvement in your method, like speed or accuracy?
I haven't seen the spectral DG results. So if Jesse, if you can send those to me, I'd like to see them. And then I don't know how we compare yet with those results.
Okay. And it was actually just one question from the general.
So maybe, but sort of related to that. In general, in the whole sort of sphere of integral equation methods,
yes.
Where do tree codes sit in terms of in terms of the overall efficiency and speed? Are these?
Well, yeah, I mean, I think the barycentric tree code is it's going to change things. I mean, I think it's going to get picked up. I mean, previously, I would say, I've been working on tree codes a while, and previously there would have been a Taylor approximation over here, and that was say analogous to the spherical harmonics, except we would use in Cartesian coordinates. And so we tried to implement the Taylor tree code on the GPU. It just was not very efficient because, again, it uses recurrence relations. Now this Scion review paper was out there for years. I knew about it. It was only about 2 years ago that I said, why don't we try to use that to make a tree code? And I think it turns out to work very well on GPUs, which is not something I thought would happen originally. But when you sit down and look at the formulas, this thing over here is really, as I said before. So I think this is going to change things. The other thing, this is kernel independent. It doesn't matter that there's a Coulomb potential over here. So in fact, in this paper with Lei Wang and Svetlana, we applied this to the what are called regularized Stokes-Lit kernels, which are very complicated kernels. And there's been very little fast summation methods for that, but the barycentric tree code works very well there. So I think if people learn about it and they try it, and these guys are making their codes available, so we'll see what happens.
Great. I don't see any more questions here, except for one more sort of general organizational question, I guess. There is a request for your overheads. And if that's okay with you, we'll get.
Absolutely. Should I
Okay.
send them to someone, or if
Yeah, I
anyone
guess
wants?
we can. Yeah, we'll gather them and make and provide them on through the MICD site and send out a message about it. Well, I don't see any more questions here. Mariana, do you?
No, other than Charlie
Okay.
Daring said it was a great presentation. So,
Okay, great.
Thank you.
Okay,
we'll
well, thanks very much, Robert. I will hand back to Mariana for a second to get us set up for the next presentation by Vikram Gavini.